Thanks for joining us today on HXGN TV. I'm your host, Kyle Phelan, and today we are discussing real-time 7DOF pose control of an industrial robotic system for machining. Joining me today is Joel Martin, Leica Absolute Tracker Product Manager at Hexagon Manufacturing Intelligence, Christian Möller, Project Manager at Fraunhofer IFAM, and Hans Christian Schmidt, a scientific researcher at Fraunhofer IFAM. Guys, thanks for joining me today.
Thanks, Kyle.
Thank you, too.
So Christian, I'm going to start with you. Can you tell me a little bit about Fraunhofer IFAM?
Yeah, sure. So the Fraunhofer Institute, IFAM stands for Manufacturing Technology and Advanced Materials. And I would like to show you a little video about what we do, particularly in two special fields. So you see in the video the first part in the automation and production technology, that is our assembly technology. And especially the assembly of large TV523 parts. So you see here, we do everything with robotics. You see the handling of big robotic parts. You will see the curing of some adhesives. We assembly everything from very small parts over medium parts up to the largest parts that you can imagine, like vertical tail planes. In this case, we make some quality management with everything with robotics. So we have different kind of end effectors on the robotics that we can apply different kind of applications with. Now here you see some adhesive bonding and some fast curing processes from very small parts. And here, for example, in a hybrid robotic system to extend the workspace of the robot. As usually, we use some Leica measuring systems, for example, in this case for gap analysis. And again, you see the handling of vertical tail planes with the robotic end effectors. So that is basically one of the big parts we do at Fraunhofer IFAM in Stade. The other one will be the robotic machining, because everything that we want to assemble should fit. And for the fitting, we need first a machining process, like milling processes and drilling processes, and therefore we attach milling spindles to the end effector of the robots. So that we can perform the drilling before we assemble parts. Here we look especially on all process parameters like the feed rate, the process forces, and especially the accuracy of the robots, because robots right now are not as accurate as they are for machining centers. We not only do TV523 parts, but we mill also aluminum parts, because that is widespread in the aerospace industry. And here in this picture, you see the robot we are using for our 7DOF control, which is equipped with a Siemens CNC control, so that we can apply additional algorithms in that machine. In this video, in this short track, you saw the TMAC in action during the 7DOF. And to expand the workspace of these robots, we mount them on mobile platforms. So the mobile platforms are able to move alongside the part. And the robot can machine in one part, and after the machining is done, he will move over to the next position and can resume the process. So we are able to machine very large parts like they are used to in the aerospace industry.
Now, with the implementation of the Leica Absolute Tracker AT960, what industry problems were you trying to alleviate?
Yeah, basically what you just saw in the video, it is the industry where you have very large workpieces. It can be aerospace, it can be the wind energy sector, or for example buses or train manufacturing. So everywhere where you have large parts, you need large workspaces, and therefore right now you are using very large machines. But that is state of the art that we want to get rid of, and we do everything with like flexible machining, and that will be robotics in this case. So we use robots for large workspaces, but the robots have one problem in comparison to the machining centers, and that is the absolute accuracy of the robots. So we want these robots in the machine instead of the machines, but we want to be as accurate as the machines, and therefore we have the solution of the external guidance with 7DOF.
Why external guidance and not the more traditional robot calibration?
Yeah, robot calibration has one big disadvantage, and that is that the calibration is only as good as the model is of the calibration. And you have different influences from the outside that are not recognized by the calibration model. So, for example, thermal expansion or unconsidered loads. And this is the last step that is needed for for a very accurate robot. So that's why we are using laser tracker systems.
Were there any other technologies involved in that, or what did you use for that?
We use not only the 8960, but we use Leica TMake to get the 60 OF measurement at first, but together with a real-time bus system, we are able to have a 70 OF with a real-time stamp. So we have a very, very precise time measurement, and that makes it possible to join the EtherCAT bus system from the laser tracker together with our Profinet IRT bus system via a gateway, so that we have our whole system together in one system. So the bus system can transfer the data from the measurement device, in this case the laser tracker, to the control. And in the control we have the possibility to use the measurement data from the laser tracker to correct the robot path in the UCI app. The UCI app is called Universal Compensation Interface, and this interface enables us to get direct access to the robot path. As you can see here in our test stand, we have the Leica laser tracker next to the robot and a TMake attached to the robot spindle. So all in all, this makes it possible for us to have a closed loop control.
Now, Joel, I'm going to come to you. You're our Leica tracker expert. Why the absolute tracker?
So we approached this in combination with the work that the guys at EPOM are doing, looked at all of the things that Christian just mentioned as far as limitations in the existing environment, robotic compensations, what robots can do, how accurate robots are, looked at what industrial manufacturing is trying to do with large part manufacturing and what the limitations are. And one of the things that we really focused on with the 18960 and 6DoF and 7DoF measurement was to be able to feed that information back into the robot control loop. So what we built was a core piece of the technology that EPOM is using to do the robot guidance, but not the full solution. It's a puzzle piece, right? So if you look at a tracker and a laser tracker at its core, it essentially measures a three-dimensional point in space over a very large volume. That's not enough to do robotic machining and robotic calibration. We needed to be able to do more than that, so the creation of the TMAC was built up. The TMAC gives us the ability, unlike a reflector, to measure not just XYZ positions, but XYZ and pitch, roll, and yaw. So that's the 6DoF that Christian mentioned. 6 degrees of freedom measurement at the end effector of a robot gives us a very precise robotic location at the end, but again, we needed to take that one step further, which is the 7DoF technology, again, that Christian mentioned. 7DoF is the 6 degrees of freedom, so it's XYZ, IJK, and adding a low latency timestamp to the data as well that allows them to take the data from the laser tracker, bring it directly into the robotic control loop, and use the drive of the TMAC at the end effector of the robot to finally position the robot control loop, regardless of what's happening behind that end effector with the robotic stack up of the kinematic model.
So Hans Christian, how does the laser tracker help you accomplish what you set out to do?
Our robot is not able to directly measure the position and orientation of the anti-factor. The encoders, the rotary encoders, are at the motors, and the Leica laser tracker gives us the ability to directly measure the position and orientation of the anti-factor. The robot has 6 independent controllers, one for each joint. At the top in the right you can see the kinematic block represents our robot arm, and the position and orientation of the anti-factor is measured by the laser tracker at the bottom. The data measured by the laser tracker is preceded by the UCI app at the left in the picture. And the UCI app calculates the joint angles from the measured data. The joint angles are fed back to calculate the axis errors of the robot. This is how the control loop works.
What are the advantages of this solution?
The big advantage of this solution is the extreme high accuracy of the robot. This is not only available for the small workspace as, for example, a calibrated robot has, but also for a very large workspace like the robot on the platform has. In the picture you can see a diagram where the accuracy, the absolute accuracy, is compared for the 3 different setups. The first setup is the robot without external guidance. The second setup is the robot with 3 DOF guidance, and the last setup is the robot with 6 DOF guidance. The 3 DOF guidance is similar to the 6 DOF guidance, but it does not correct the orientation. Instead of the TMAC, it uses a simple reflector. The mean errors with 3 DOF are only a third of the errors without external guidance, and the maximum errors also decrease. The errors with 6 DOF control are very, very small. I must say that I was really impressed when I saw these results the first time, because we tested different robots at our institute, and none of these robots reached such a high accuracy. Yes, and the control loop is able to compensate all errors of the robot of low frequencies. For example, errors due to the errors of the kinematic model of the robot.
Can you give me examples of errors of low frequency?
Yes, a good example is the thermal expansion of the robot. If the robot does many movements with high accelerations, the motors become hot and heat up the rest of the robot structure. Yes, this can lead to deformations up to half of a millimeter, and this can completely be compensated by the laser tracker control loop. Another example is a milling process where the process forces lead to deflections of the robot. And we did a milling test where most of these errors could be compensated.
Are there any positive side effects of laser tracker utilization?
Yes, I think a big problem in aircraft industry is to reference the workpiece, to measure where the workpiece is. And our laser tracker in the control loop can not only be used for the external guidance, it can also be used to measure the position of the workpiece. For example, we used a simple reflector to judge some points at the workpiece and measure the positions. Another, maybe more flexible approach would be to use a T-probe, because the visibility would be improved.
Christian, I'm going to come back to you. Where do you see applications for 7 DOF guidance?
Yeah, like Hans Christian mentioned before, there are every facility or every industry where you have large workspaces, you can use laser trackers because they are already there. Especially when you talk about the factory of the future, like you heard multiple times in different keynotes here. You have flexible machining, you have flexible holding fixtures, everything is moving on mobile platforms. You don't want to have a static shop floor anymore. So for all these applications you already need a laser tracker. And why not guide then the end effector of the robot? For example, we had the possibility to join with a big OEM who wants to increase its cycle times of drilling processes. So he wants to drill in a large workpiece thousands of holes. But before every hole, he needs a small referencing process which takes some seconds. So if we can get rid of this referencing process by continuously guiding the robot to its exact position with high accuracy, then we will save a lot of time.
What are your next steps from this research?
Hans Christian mentioned the errors of low frequency, but there are still some errors of high frequency. So when you go in very fast machining with a path who is changing very fast, and maybe the natural frequency of the robot is excited. These are frequencies that the robot control, like it is right now, cannot control anymore. So our idea is to attach a second end effector which is a very small parallel kinematic, like a hexapod, which can provide very fast movements and very precise movements. We want to attach that at the robot end effector, in between the spindle and the robot. So this kinematic can do the fast movements, and the robot will do the big movements. So with this, we come to a solution that brings us a very, very fast and flexible overall solution, where we can already use the 7 DOF control we implemented here.
Guys, thanks for joining me today. For more information on Fraunhofer IFAM, visit efam.fraunhofer.de. To tune into additional episodes of HXGN TV, tune into hxgntv.com. Thanks for watching.